Okay, this is our first session over kinematics, so we're going to jump right in. We'll talk about content as we need to, and if you'd like to, go ahead and pause as necessary as you're going through things. So here we have a free response problem. This was actually on an AP test. We've got two identical spheres. They're going to be released from a device at time equals 0 from the same height, like you see in the picture. Sphere A is going to drop straight down, has no initial velocity, whereas sphere B is given an initial horizontal velocity of v0 and travels a distance d before it reaches the ground. They reach the ground at the same time, that's supposed to be tf, even though sphere B has more distance to cover before landing. Air resistance is negligible. So, the dots below represent those spheres. We're going to draw a free body diagram showing and labeling the forces acting on each sphere at that final time over 2, so halfway on the ground. So sphere A is going to be here, sphere B is going to be there. That's what that free body diagram is going to represent. Now, when we draw a free body diagram, let's be very careful about it. All right, so as we do this on the AP test especially, forces must start on the dot representing our object. And then they must point in the direction of the force. The size matters here. So the length of the force needs to be proportional to the size of the force. We'll see that in a different session a little bit more. This is mostly kinematics, but right now we're just drawing the force. And then what's very, very important is that there's no components on this drawing. Sometimes forces point to the left at an angle, and our general strategy is to break that force up. We're not going to do that here on the specific free body diagram that the College Board asks for. Another thing about free body diagrams is that we only draw forces. That means no velocity. That means no acceleration. The only thing that we should be drawing on this is forces. Now, looking at these two spheres as they fall, while they're in the air, especially when we're talking about projectiles, the only force acting on them is the weight of the object itself. So, for sphere A, the weight is straight down because weight only pulls down towards the middle of the Earth. And for sphere B, even though it's moving to the side, its weight is straight down. They're identical, so those two things had better be the same size. The big idea here is that once we're in the air as a projectile, the only thing acting on this is going to be weight. It's the only thing that matters, especially since we were told that the air resistance is negligible. The second thing is a graph of the horizontal component of the velocity. So, fancy way of saying the sideways velocity. As time goes on. Now, looking at what happens, sphere A is dropping straight down. So if we look at sphere A, this is a way that I like going through problems. If we look at sphere A and we look at its x direction and its y direction, we're going to notice some things that we're given that may help us out here, right? So for sphere A as a projectile in the x direction, the initial velocity is 0 because it tells us it's falling straight down. The acceleration is 0 because there's generally no acceleration in the x direction for a horizontal projectile. And because of that, the final velocity is going to be 0. And we're all talking about horizontal stuff. So if we look at this, for sphere A, we have no horizontal velocity. And we have no horizontal acceleration. So all the way through, because there's no horizontal velocity, sphere A is just going to be sort of a line along the bottom until we get to our final velocity. That's what sphere A looks like, and we should label that. We want to know that this is for sphere A. For sphere B, again, since we're looking at the x stuff and the y stuff, for sphere B in the x direction, we have some initial velocity, which is great, but the acceleration is 0. So for sphere B, we have constant horizontal velocity, but it's not 0. And my slope should be flat for this whole time. So sphere B has some constant velocity the entire time. Sphere B is going to look like that until we get to T final. That's what they hit the ground. So, and then we got to label it. That's what's going on for that. Now, the next part of the question is asking, why do they hit the ground at the same time, even though they cover different distances? So before we do that, I want to look at the y information for each one. So for sphere A in the y direction, the initial velocity is 0 because we're dropping it at rest. The acceleration is gravity. We're just going to call it g, and it's straight down. And the distance it's falling in the y direction is capital H, again, straight down. That's everything that's going on in the y direction for sphere A. For sphere B, if we look specifically at the y direction, this means we're going to ignore all the x velocity because, and this is really, really important, the horizontal and vertical velocities well, not just velocities, the horizontal and vertical motions are independent of one another. They happen without affecting the other. So even though we start off with an initial velocity in the x direction, the initial velocity in the y direction is 0. If we just look at that in terms of the y direction, that object is just falling from rest in the y direction, has no upward velocity. And in the y direction, the acceleration is g, the acceleration due to gravity, straight down. And in the y direction, my displacement is h, straight down. So because the horizontal and vertical motions are independent, B and A have all the same y stuff. Because they have the same y stuff, and I can find time in the y direction with that stuff, they're going to have the same time, even though their x stuffs are very different. Now that's the answer to this next question. In a clear, coherent paragraph length response, explain why the spheres reach the ground at the same time, even though they travel different distances. Include references to your answer to parts A and B. So we want to talk about that graph, and we want to talk about the free body diagram. And we will. Now on the AP test, this is a very specific kind of question. Paragraph length response. A paragraph length response is always worth 5 points. worth 5 points. 4 of those points are for logical reasoning of the problem. The last point is a paragraph point. Now, paragraph point is not super specific. What that really means is answer is mostly prose in nature. You can use diagrams, you can use equations, but those need to largely supplement the words that you're using. And here, it doesn't have to be a paragraph specifically to get that point. Bullet points are okay. It doesn't even have to be complete sentences, but you need to have full and complete thoughts and full and complete logic to go through this to get that paragraph point. One of the things that I try to tell my students as we go through this is that the 4 points for logical reasoning mean you have to have at least 4 different things to say to get to your answer. We want it to be reasonable and clearly thought out. Now, it's important to answer the question before you begin doing the paragraph stuff, right? So looking at it, we've already answered the question. We talked about the why stuff, how all the why stuff was the same, and we talked about how the horizontal and vertical motions are independent from one another. But when we do paragraph length responses, it's not going to be enough to just say they've got the same why stuff, so they have the same time. When we do these paragraph length responses, we need to be specific about what the why stuff is and what the things that we're talking about are. So the big idea that started us off was that horizontal and vertical motions are independent of one another. This is important because what it's telling me is that the horizontal velocity of B does not affect the time to fall. Horizontal velocity of B is the horizontal thing, and time to fall happens in the y direction. So we've established that now it doesn't really matter that B has a horizontal velocity. It's going to in no way affect how long it takes to fall. That is one point. That is a good point to make. So now we need to talk about how each ball does fall, right? So each ball has the same y distance to fall. Each ball has the same y acceleration as it falls. You don't have to go into necessarily because all objects that fall have the same acceleration due to gravity when air resistance is ignored, but it's not bad to say that. Same y distance, same y acceleration, and they both have the same initial, too many eyes. They both have the same initial y velocity. Because all of those things are the same, each ball is going to fall with the same time. So it's very important on these paragraph length responses to think that if something is constant, say so specifically. Right. If values are equal, don't summarize what those values are. List specific values as you do so. Those are the two big mistakes that I see people making on this, both in my class and on the grading of the AP exam. Students aren't specific enough about mentioning this value is constant, everything else is changing. Be specific about what that value is. Or instead of saying they have the same y distance to fall, each ball has the same y acceleration, each ball has the same initial y velocity, students are prone to say things like, all of their y information is the same, so I need to know what that y information is. It's not good enough just to say all of it's the same. That's in no way specific enough to answer the question. So for a paragraph length response, be specific. Very, very important. All right, we've got Jim and Sarah. They're on the moon because why not? So Jim is going to put his arm over a cliff edge and throw a ball straight up with a speed of 20 meters per second. Sarah is going to throw an identical ball with the same initial speed of 20 meters per second, but she's going to throw the ball at a 30-degree angle above the horizontal. We have a few questions to answer based on that. Best thing to do at this point would be pause and answer the question. So, let's talk about the greater vertical velocity. We got to decide who has the greater vertical velocity. But it's at the highest point in its trajectory. That's really, really important. At the highest point, which ball has the greatest vertical velocity? So, at the highest point, each ball is momentarily at rest in the y direction. In the y direction, objects go up, come back down, and their velocity is temporarily 0 at the top. And since we're just talking about vertical stuff, I don't care about what's going on in the x direction because, like we said before, x and y motion are independent of one another. They're independent of one another, so it doesn't matter that Sarah's ball has some horizontal velocity at the top. Vertically, in the y direction, that ball is stopping and turning back around. So they're both going to be the same. The next question is still asking about the top, still looking at the highest point, but now we want to know who has the greatest horizontal velocity. So now would be a good time to probably draw what Jim and Sarah's projectiles are doing. So we're at a cliff on the moon. Probably doesn't look as sharp as that. Jim's ball, 20 meters per second, straight up, straight down. I gave it a little, but it doesn't matter. And up here we said the velocity was 0. Sarah's ball, on the other hand, is thrown at an angle. It's still 20 meters per second, but it's thrown at an angle and it comes back down. A really good parabola, but lands over here. And at the top, the y velocity might be 0, but Sarah has some x velocity. If we really look at what's going on, because Sarah's ball is thrown at an angle, we have 20 meters per second at a 30-degree angle above the horizontal. She has some velocity in the y direction to begin with. She has some velocity in the x direction to begin with. Now, since the acceleration is 0 in the y direction, this x velocity never changes. So when we're at the top, Jim is at rest because he has no horizontal velocity at all. Sarah's x velocity never equals 0, even at the top, which means at the top, Sarah has the greater horizontal velocity. Part 3 here is still at the top. It's important not to forget that. At the top, we said that the velocity was 0 in the y direction for Jim and 0 in the x direction for Jim. For Sarah, we said that at the top, the velocity was 0 in the y direction and her velocity in the x direction was not 0. So Jim's velocity vector looks like a dot because Jim has no overall velocity. Sarah's velocity vector has 0 for a y component, so we don't need to draw anything up and down, but she does have some x velocity. It's that size. So this would be her velocity vector. Her total velocity is velocity in the x direction. Put all those things together. So Sarah is going to have the greater magnitude velocity at the top. Now, each ball just before it hits the ground. That's what part B is. There's only one question to this. So it's 50 meters below where we released. And now we want to know which ball has the greater vertical velocity. So for both of them, in the y direction is going to look like, just look at all the components and see how we would find out how fast each one is going in the vertical or the y direction. So in the y direction, we're going to have an initial velocity to deal with. We'll just call it v0. That might be different for each one. I don't know yet. I just want to look at overall what's going on the y direction. The acceleration is whatever the gravity on the moon is down, and our delta y, even though each ball is going to go up and come back down, this is my displacement in the y direction. Displacement is just the distance from the start to the finish. So if I look at just the displacement, it's going to be 50 meters down. So if I wanted to look at my final vertical velocity, it would be velocity squared plus initial velocity. Velocity squared equals initial velocity squared plus 2a delta y. Now my initial velocity is up, so that final velocity is going to be the square root of initial velocity squared plus 2 times negative g times negative 50. It's going to bleed over into the next question. That's okay. So it's the initial velocity squared plus 2 times g times 50. This part, because each ball falls with the same acceleration and each ball falls with the same distance, is the same for each. So I'm not concerned with that contribution. So what really matters is the initial velocity in the y direction. That's worth stating. Only the initial velocity in the y direction matters. The ball with the greater initial velocity in the y direction is going to be the ball with the greater vertical velocity just before it lands. So, only the initial velocity in the y matters. So we got to figure out what that is. For Jim, the initial velocity in the y direction is 20 meters per second because he's throwing his ball straight up. So all 20 meters per second are straight up for Jim. For Sarah, again, she threw at an angle. So she's got 20 meters per second here. She did that at a 30-degree angle. So we can figure out what her velocity in the y is, but really, it's just important to know that because 20 is the hypotenuse of that little triangle, her velocity in the y direction is less than 20 meters per second. So Sarah's ball has a smaller vertical velocity to begin with, so she's going to have a smaller vertical velocity to end with. Jim gets to win this one. Jim has a greater vertical velocity at the end because he started off with a greater speed. Now, if we want to find that piece, we got to do a little bit of trig. I'm going to try to make it a little bit easy for you. If that's my angle, that's the opposite side. The opposite side is the side not touching the angle. The size of the opposite side, in this case it's Vy, because we're talking about opposite, not because we're talking about the y direction, is going to be the hypotenuse. Well, here, we'll just say this. Opposite side is always going to be the hypotenuse times the sine of the angle. So in this case, the opposite side is velocity in the y direction. The hypotenuse is 20 meters per second times the sine of 30 degrees. So that velocity in the y direction is 10 meters per second, which is less than 20, which is why Sarah's ball is moving more slowly in the y direction at the very bottom. Okay, part C, removed from those, well, we're going back to the peak of the flight. Part C wants to know which ball reaches the peak of its flight more quickly after being thrown. So, we're going to kind of do the same thing that we just did and look at, we'll break it down. We'll do Sarah's information underneath of Sarah and Jim's information underneath of Jim. So we're going to look at the y direction stuff. We can use real numbers here because we just kind of figured everything out. So for Sarah, her initial velocity in the y direction was that little part, and we said that that little part was 10 meters per second. So part of her 20 meters per second, 10 meters per second in the y direction, and that's up. Her acceleration is the moon. So we're just going to call it g on the moon. It's 1/6 of what we have. Doesn't matter what that is. And the delta y, well, and then at the very top, the final velocity is 0. So the equation governing that, putting that all together, we don't have to do the equation. We'll talk about the equation in a second. So Jim, on the other hand, starts off with an initial velocity of 20 meters per second up. Same acceleration, whatever the gravity is on the moon, down. And at the very top, they stop, they're at rest. 0 velocity, like we said for part A. So just looking at this, Sarah starts off at 10 meters per second, has some acceleration, and stops. Jim starts with a bigger velocity, has the same acceleration, and then stops. Because Jim starts with a bigger velocity, it's going to take more time for Jim to stop. So Sarah stops first. If we wanted to do that a little bit more mathematically, that equation has all of our stuff in it, v equals v initial plus at. So if we solve that for time, v minus v initial over whatever the acceleration is equals the time. And since the final velocity is 0, negative initial velocity over the acceleration equals time. So for Sarah, that's negative 10 over the gravity on the moon is equal to time. For Jim, that's negative 20 over the gravity equals time. It's a longer time for Jim because he has a greater initial velocity. Because this question isn't long enough, we've got a graph. Here's a graph representing the vertical velocity of Sarah's ball. On the same axis, sketch a graph of velocity versus time representing the vertical velocity of Jim's ball. So, every time we see a graph, I want us to think about a couple of things. This is a velocity versus time graph, so what is the slope of this graph? What is the area of this graph? This is an every time you see a graph thing. It is the smart thing to do as we're going through problems. What is the slope? What is the area? And even before getting into this graph, for the slope, we're always looking at rise over run. The y value over the x value. That's going to be how we calculate the slope. That's how we're going to find out what it is. When we're looking at the area, if we imagine it just as a square, obviously here there's a triangle, but in general, whether we're doing 1/2 base times height, we're always doing base times height. Maybe times 1/2, maybe not. It just depends on the shape of the graph, but we're always multiplying the x times the y. So for any graph, that's a good way to figure out what the slope represents, and that's a good way to figure out what the area represents. Now here, for this particular graph, and we should already know this, but the slope is velocity over time. And in general, velocity over time is acceleration. So the slope of this graph is acceleration. And then the area for this graph is going to be velocity times time. And in general, velocity times time is displacement. And I said this was vertical. So that's our delta y. So our area total for the graph is going to be delta y. And the slope is going to be the acceleration. So that's good to know. So this graph shows Sarah's ball. And I know that the slope here is acceleration. And since we're a projectile, the acceleration here is the acceleration due to gravity where we're at, or the acceleration due to gravity on the moon. Jim's ball, because that's what we're supposed to sketch, has the same acceleration so Jim's ball has the same slope as Sarah's ball. We're going to need to draw a parallel line as we do this. I brought a ruler. You can bring a ruler to the AP test. That is perfectly allowed. Now, the next thing that we need to look at, the area is not going to help us out so much here, but this represents Sarah's initial velocity. I know that Jim has the same slope, so it's going to be a parallel line, but Jim starts off with a greater initial velocity than Sarah does. So because we're talking about the vertical direction, we know that Jim starts off with a greater initial velocity. So Jim has a greater initial velocity with the same slope. So Jim's motion is going to look something like that. Same slope, so it's parallel, and Jim has a greater initial velocity, so he starts off at a higher number. So let's look at what this means for some of the questions that we've already answered. This is a good way of going through that. So for some of the questions that we already answered, part A wants to know at the highest point in their respective y directions, who has the greater vertical velocity? Well, at the highest point, that's the point where we're going to have the greatest positive displacement before we turn around and go back. This represents positive displacement. That's positive area. And this begins negative displacement. So our highest point for each object occurs right before we flip over the time axis. This is telling me that at that highest point, at my point of maximum positive displacement, both Jim and Sarah have the same both Jim and Sarah have the same velocity of 0 at that point. Can't answer anything about horizontal velocity from a vertical velocity graph, so it doesn't really help me on number 2 or 3 for that first one. Just before they hit the ground, who has the greater vertical velocity? That would take a little bit too much with this. And then who reaches the top more quickly? That's the top. Sarah gets there first as far as time is concerned. Just a few things that you could do with that graph. All right. Now let's move on to the... Oh, we have more. I like this one. So here we've got 2 stones dropped from the same height at an amusement park ride, and we want to know one is dropped later than the other one. And we want to know, while both stones are falling, how do the speeds of A and B compare? So now would be a good time to pause and try to think about all the things that are happening as these 2 stones are falling when they're off by 1 second. All right. We're back. What I like to do on a question like this, we don't have any numbers, but we do know that they're falling, and we do know that they're falling a second apart. So I kind of like to draw what it looks like as each of these objects falls. So we've got ball A, we've got ball B, and they're dropped from the same height. So we'll say that this is the height that we're falling from. So ball A starts off at rest, time equals 0. After a second, ball A falls a little bit. In the next second, ball A falls more. After 3 seconds, it falls even further. And that pattern continues. Well, ball B starts off up here, but we hold ball B for an entire second before we drop it. So for ball B, it's at the starting point for time equals 0 and time equals 1. Then it begins to fall. Now, when things fall, all of their y information is identical. So after 1 second, because ball B has the same acceleration as ball A, after 1 second, ball B will fall the same distance that ball A fell in 1 second. But he started off at 1 second, so this is overall time of 2 seconds. He falls the same distance in the next second. He's just a second behind. So ball B is always 1 second behind ball A. The best way to look at what's going on is to compare where the balls are at the same time. So at 1 second, each ball is at that little green highlighter spot. At 2 seconds, each ball is at the yellow highlighter spot. At 3 seconds, each ball is at the blue highlighter spot. That pattern's going to continue. Now, hopefully you can kind of see what's going on. Now, before we do anything else, we can talk numbers a little bit, especially for velocity. I know that velocity is initial velocity plus acceleration times time. So at the beginning, ball A starts off with an acceleration of 0. Sorry, a velocity of 0. After 1 second, that's going to be acceleration times time, or 10 meters per second. After 2 seconds, it's acceleration times 2 seconds, or 20 meters per second. After 3 seconds, it's acceleration times 3 seconds, or 30 meters per second. Basically, anytime we're here, the ball is going to be traveling at 10 meters per second. Anytime we're here, the ball will be traveling at 20 meters per second. Anytime we're here, the ball will be traveling at 30 meters per second. So after each ball has fallen the same distance, it should have the same velocity. That does not mean that that happens at the same time. I'm going to draw some connecting lines. At 1 second, ball A has fallen a distance shown and has a velocity of 10 meters per second. At 1 second, ball B has not fallen yet and has a velocity of 0 meters per second. At 2 seconds, ball A has fallen the distance shown and has a velocity of 20. Ball B has only fallen the first distance, has a velocity of 10. After 3 seconds, ball A has fallen this far because it's been falling for 3 seconds and has a speed of 30. Ball B has only fallen for 2 seconds because he's a second behind and has a speed of 20 meters per second. So that little picture is helpful. Let's go answer some of these questions and see if it helps. While both stones are falling, how do the speeds compare? So at any given second, so let's say at 2 seconds, ball A is traveling at 20 meters per second, ball B is traveling at 10. At 3 seconds, ball A is traveling at 30, ball B is traveling at 20. So stone A is faster because it has been falling for a longer time. Because it's been falling for a longer time, and velocity is initial velocity plus acceleration times time, it's going to have a higher velocity. It's going to be going faster. Ball B is always a second behind. Does the difference in speeds for stone A and B increase, decrease, or stay the same as they both fall? Let's look at it. At 1 second, stone A is 10 meters per second faster than stone B. At 2 seconds, A is 20, B is 10 meters per second faster. At 3 seconds, we have 30, 20. It's 10 meters per second faster. The difference stays the same the stones are always 1 second apart in time falling, and because velocity is proportional to acceleration times time, stone A is always basically acceleration times 1 second, or 10 meters per second faster than stone B. Will the separation of the two stones as they fall increase, decrease, or stay the same? And this is where it's really nice to look at this picture. This is my separation between here and here after 1 second. This is my separation after 2 seconds. This is my separation after 3 seconds. It appears as though it appears as though separation increases. And here it might be, in order to explain it, a little bit more helpful to look at an equation. So as we fall, delta y is v0t plus 1/2 at squared. Started off with an initial speed in the y direction of 0, so delta y is 1/2 at squared. So displacement is proportional to t squared. These objects are always separated by 1 second of falling time, but the difference between 1 squared and 2 squared is only 3. And the distance between 2 squared and 3 squared is 5. Right? So instead of being linear, where they're always a times 1 second apart, that t squared means that as time goes on, t squared is larger than t minus 1 squared. Increasingly, that gets larger and larger. Whereas as time goes on for velocity, the distance between t and t minus 1 is always 1. Here that distance is bigger. Will the time interval be equal to, greater than, or less than 1 second? Equal to 1 second as far as when they hit the ground. B is always 1 second behind A. All right, let's move on to some multiple choice. And cover a few of these. So I'm going to move quickly through these. It's in your best interest to pause before each question. Give yourself some time to answer it, and then hear the explanation. I'm just going to go straight through. I might give 2 seconds pause before it. So now would be a good time to pause for question 1. A toy dart is fired straight up into the air, ignoring air resistance when the dart reaches its maximum height. So straight up into the air, that tells me that there is no x velocity, and the maximum height, sorry about that, at the maximum height, the y velocity is equal to 0. So the velocity is 0 meters per second at the maximum height because there's no x velocity and the y velocity is 0. Question 2, toy dart's fired into the air and it returns to its original position. You really don't need to read anything else. If you see the words returns to original position and displacement, the answer is always 0. The displacement for a round trip is 0. Displacement is the distance from the starting point to the ending point. So if we return to our original position, there is no distance between the beginning point and the ending point, so our displacement is 0. All right, Triumph sports car accelerates uniformly from rest to a speed of 30 meters per second in 6 seconds. Now, if you use just equations with this, and I can show that, I will show that, you have to find the acceleration first, and then you find the distance. There is another way to do kinematics problems, especially when you don't have acceleration. In fact, this is a good rule to have. If the acceleration is not given, use a velocity versus time graph. These are nice because, and we talked about this earlier, slope is equal to acceleration. Area is equal to displacement. We can use those ideas with a velocity versus time graph to solve almost any kinematics problem where we don't have the acceleration. We can use it when we have the acceleration too, but it's particularly powerful when we don't have the acceleration given. So if we do velocity versus time, when we start off at rest, that means my initial velocity is going to be 0. We accelerate uniformly, which means I have a constant acceleration to a speed of 30 meters per second in a time of 6 seconds. So I've got all the information that I have in the problem on this graph, and I want to know the distance the car travels. So the distance that the car travels is the displacement. That's the area. Well, that area is the area underneath the velocity curve, or in between the velocity curve and the time axis. So it's that triangle right there. So it's 1/2 the base of the triangle, 6 seconds, times the height of the triangle, 30 meters per second. That makes the displacement 1/2 times 6 times 30, or 90 meters. Using the graph is usually a much quicker way to go through a problem where you don't have the acceleration. If you wanted to use equations to go through that, show that too. List out our givens. The initial velocity is 0. The final velocity is 30 meters per second. The time is 6 seconds. The acceleration is unknown. And ultimately, we want the delta x. Step 1 is always find the acceleration. So for step 1, I want the acceleration. I have the initial velocity, the final velocity, the time, and I want the acceleration. Well, those are all together in v equals v0 plus at. Solve that for the acceleration. v minus v0 over the time. So the acceleration is equal to 30 minus 0 over 6. The acceleration comes out to be 5 meters per second. So now that we know that, we can move on to step 2. Step 2 is find the displacement. Now I have everything. So displacement is v0t plus 1/2 at squared. No initial velocity. So my displacement is 1/2 times 5 times 6 squared. You can plug that into your calculator, but you get 90 meters either way. I really prefer on 2-step kinematic problems to use the graph. I think it's the best way to go. All right, number 4, we're going to drop a ball from the top of a building. There is no air resistance, and I want to know the height of the building after it falls. So this is a strictly y direction problem. The initial velocity in the y direction is 0. The acceleration is not unknown. The acceleration is about 10 meters per second squared down. My delta y is the height of the building down. And the time it takes to fall is 4.5 seconds. So here we're just solving for delta y. It's one step. We have initial velocity, acceleration, delta y, and time. Delta y is initial velocity times time plus 1/2 the acceleration times time squared. So delta y is 1/2 times 10 times 4.5 squared. And that comes out to be roughly 100 meters. Now, A little bit bigger than that. Number 5 is a really, really good question. So it's asking about the initial horizontal component of velocity, and it's telling me what's going on at the highest point in the trajectory. If we draw a long arcing trajectory like that, we know some stuff about the very top. Namely, we know that the y velocity has to be 0 at the very top, because at the very top the object is turning around. So the y velocity at the top is 0, and it tells us that the x velocity at the top is 200 meters per second. Because there's no y velocity, all of the velocity is 200 meters per second. So the x velocity is 200 meters per second. But in the x direction, the acceleration is 0, so the velocity is going to be constant. Which means at all points during the travel, the velocity is the same thing. So if the velocity at the top is 200 meters per second in the x direction, the velocity somewhere in the middle here in the x direction is 200 meters per second, and the initial velocity in the x direction is 200 meters per second. Which of the following is not true of a projectile launched from the ground at an angle? So for a projectile launched from a ground at an angle, not true. Horizontal velocity is constant. That's true because the x acceleration is 0, and so the x velocity never changes. The vertical acceleration is upward during the first half of the flight and downward during the second half of the flight. Well, no. We know for a projectile that the acceleration is the acceleration due to gravity. That's always down. So the acceleration is not up then down. So that's definitely false. Horizontal acceleration 0. We said that was true. Vertical acceleration is negative 10 meters per second squared. For that never changing, that's true. And the time of flight can be found by horizontal distance divided by horizontal velocity. Now this one a lot of students like to choose. That's false. That's a true statement. So in the x direction, since the acceleration is 0, we have a velocity and a displacement. What we have here is that displacement is velocity times time. We would usually have a 1/2 at squared out here, but that's gone because we don't have any acceleration in the x direction. So our time of flight can be that displacement in the x direction divided by the velocity in the x direction. So that's true. The only thing that's not true is that the acceleration changes direction. It does not. So number 7, we have a tennis ball thrown upward at an angle from point A. It follows this trajectory, and I want to know how the x components and the y components compare at points B and C. Again, the acceleration is 0 in the x direction, so we have constant velocity. So at points B and C, the x velocity should be the same. That's answer choices B and C. It's definitely not going to be D, definitely not going to be E. If we get to the top, though, we know at the top that the y component of velocity is 0. So the y component is 0 at C. And that's all we've got. Okay, so your teacher has the answer to the rest of the multiple choice questions if you are interested in looking over those, but this is our time. So thank you very much for listening.